This is Wenzhou, and in today's presentation, I'm going to talk about a review for the paper, Who Are You? A Statistical Approach to Measuring User Authenticity. Here is the authors for the paper. So the authors is from LinkedIn group, and the author indeed used some of the LinkedIn real data to test the model. So what's the problem in this paper? It's about the password. When user enter password or credentials to a web server and trying to log in, if the credentials are not valid, of course it will be denied directly. However, if the credentials are valid, should we just accept the login? Actually, according to the paper, it's not. There are three cases. The first is access granted, the other one is denied, and the third one is more information required. This paper is trying to address whether the action should be taken when the credentials are correct. So why correct password does not equal access? Even the user knows the password, it may be an unauthorized use. For example, you tell your friend the password for one website, and he may try using the password to log into another website. That's unauthorized use. The other one is password phishing or stolen. It's likely you click some phishing email and lost your password to the hacker. The third one is your password may be correct, especially weak passwords. It's very easy to be cracked by some software. So definitely we need more verification even when the password is correct. There are two typical methods. One is CAPTCHA. And in this method, the server give you a challenge and you're trying to solve it. For example, here you need to type the character you see in the image. Another method is two-factor login. For example, in Canvas website of Georgia Tech, after you enter the correct password, you will be required to send the push or verify your identity using phone. These two methods are actually very effective to reduce the number of unauthorized logins, but there are problems. It will make the user experience very poor. For example, especially CAPTCHA, sometimes it's so difficult to read the image, and will make the user experience very bad. So the paper proposed some existing data can be used for authenticity. The first one is the request data. That obvious IP address is one of the most important, and from IP address you can derive the ISP. It's the internet service provider. For example, this IP may be provided by ATT, and also you can derive country information from IP address. Another important aspect is browser data, which browser you use. If a user usually log in from Chrome, and if he try to log in from IE, then there need additional verification. Also, the time of the login. For example, if it's 3 a.m., the user is trying to log in, that's questionable. Also, the cookies in the cookies stored in the user's computer can be used to authorize the login. If the cookie shows the user have log in from this computer a lot of times, then it's okay. And then it's reputation score. So what is reputation score? It's the same as actually the same as the reputation of a person. There are some person have good reputation and you should trust him more, and sometimes some person have bad reputation and in this case you should deny it. Similarly, here we are talking about the reputation of IP address. The IP address will indicate how likely the IP is to be abusive. And this reputation of IP address can be obtained from internal site-wide abuse data or from third-party provided data. And if the reputation of a particular IP address is not available, we can instead use the reputation of the ISP, but it's usually less accurate. Also, the login history of the user is obviously quite important, and there are many other criteria you can use. So the main contribution of the paper is actually the reinforced authentication model. So the advantage is it only uses the per user and global login history, and also reputation score, and it doesn't need the account compromise data. This is a big improvement because for most user accounts they have never been hacked or compromised, so this kind of data is usually not available, and in this scoring model the author didn't use that. Here is a simplified equation of the one we see above. So the left part is the probability of attack for a certain user with feature set of X, and is divided by the probability of legal login for this user with feature set X. So if the ratio is larger, that means it's more likely to be attacked. This part is the probability of attack with feature X, because it's usually not readily available, as we discussed in last slide. This can be used as this can be replaced with the reputation score. And this probability X is the global likelihood of seeing data X. Clearly, when you see this feature a lot globally, like from other user account, that means it's questionable. It's likely someone trying to log in multiple user accounts. And this bottom is probability of seeing feature X in the users in this particular user's history. If this probability is larger, it's a good sign. That means the user logging from here quite frequently. This part, the likelihood of user to be an attack, you can interpret as the value of account to attackers. If the value is bigger, then it's more likely to be an attack. The bottom is the likelihood of member U login, and if it's larger, that means it's more likely to be legal. From previous discussion, we actually assuming that all the features have the same weight, but in reality it's not the case. Some features are more important. For example, IP seems more important than like a user agent, and weights from, and so we can further improve the formula by assigning weights to each feature. And we can do this using logistical regression of the known data, but it must have labeled data. It must be from some account with attack history. So we can learn the weight and incorporate the weight into the equation. This is the final equation in the paper. Besides, we can use a technique to technical smoothing to handle sparse data. So this is trying to solve this problem. If the user log in from IP address that is never observed in the user history or even in the global history, then the PRX and PRXU will be 0. Is this part. Global likelihood of seeing data X will be 0, and the bottom part will also be 0. This creates a problem for calculating the overall login score. So the smoothing technique used here is original from the N-gram natural language processing model, and the basic assumption is for those unseen events like unknown IP address, you still have probability greater than 0. That's actually quite obvious. But how to calculate them? We can deduct the probability from the seen event and distribute distribute to unseen events. That is, we didn't calculate the probability of unseen directly, but rather from the seen events. That's similar like a Robin Hood principle. It's taking from the rich and redistribute to the poor. So when the IP address is not ready well, how do we estimate the probability? We can use ISP data or country level data to estimate the probability. And clearly, if an ISP is known, that means it's a higher weight. So here is an example of smoothing probabilities estimates for unseen IPs. The graph here, the black one means it's known country or ISP or IP. C means country. This is country 1, country 2, country 3, ISP 1, ISP 2, and IP 1, IP 2, IP 3. And the number in parentheses means how many times it was observed. Of course, the more frequently it observed, the better. And in the bottom graph, we added some unseen IPs. Like this IP is unknown, this IP is unseen before. And from the globally, if you look at this row, there are 9 IP that we have known, and also there are 9 unknown IP. So for each unseen or unknown IP, the probability is 1 of the 18th. But if we utilize the country data here, if an IP belongs to the country 1, we have in country 1 we have 5 known IP and 3 unknown IP. So the probability of IP level is 1/8. And we look at the country level. This country happens more frequently, but the total country count is 5 plus 3 plus 1. So it's it's 9. So the country level will be 5 divided mass, and you times them together to get the probability of this unseen IP. Similarly, for if the IP is from country 3, this 3, you have the probability of unseen IP is 1/3 because you only have 3 IP here, and the probability of this country is 1/9. So you can see now the unseen IP from country 1 and country 3, they will have different probability. That's how this smoothing works. Here is the overall structure of the proposed system by this paper. If the user enters credential, and if the credential is not valid, of course it's denied. But if it's valid, we will use the scoring model based on the equation provided in previous slides. And this scoring model will take it's created by using the training data and also the label data from investigation team. These are manual labels. Also, the feature attributes can be used for the training and the scoring model. And after the scoring model give a score, we can make a decision whether the access should be granted or further information is requested or it should be denied. And if the history is if the access is granted, we need to update the user's login history. This slide shows the effect of some of the example features. Some of the author actually used the LinkedIn data to test its model and have some interesting findings. For example, the country information of the login alone can be very helpful. For example, for botnet, if botnet only 1% of the botnet attack can have country match. But so that this criteria alone is quite effective to remove botnet attack. But for compromised accounts or legal accounts, it's not quite effective. It's most likely, in my opinion, this is maybe a bit biased because LinkedIn is a US company and most of login are from US, so it's quite likely a lot of the country, a lot of login are from US, so it's not a very strong classifier. But for botnet, because it can distribute all over the world, the country will be very helpful. The bottom table shows the effect of IP address and UA is user agent, like which browser you are using. You are using Chrome or Firefox. The third one is the combination of these two features together. And the bottom one is adding weight to IP and user agents. And the number shows here are true positive rate. TPR is true positive at 10%, FPR, false positive rate. So when we fix a false positive rate, the higher the true positive rate, the better. And these three larger column are different smoothing models. I'm not going into the details, and the arrow here is the level of the feature hierarchy. For example, for IP information, the first level you can simply use country data, and if you use ISP data, that's another level. Then it should be more accurate. And indeed, we can see here is the best performance the author can get is using weighted feature for IP plus user agent. You get 98% true positive rates. The author also studied how to evade attacks. The paper classified the attacker into different categories based on their knowledge. The first one, password only, it also called dumb attack. It's like it's from a single IP and different user agents. This attack obviously is quite easy to block. And then another large category is botnet attacker. Because there are so many botnets, it can have a lot of different IP and different agents. There is a much higher chance to successful login. And the researcher attacker, that means that researching attacker, that some people basically know the target is country information, so the country filter will not be helpful. And the phishing attacker, this is probably the most complicated attack because it has both the IP information and the user agent data, so you can mimic this login information and trying to attack. We can start with this column, true positive rate at 10% FPR. It's actually all of them. The training model works quite good. The phishing is a bit difficult to detect, and in real world, the compromised account is usually more difficult than bottleneck, because bottleneck, the country information alone is able to filter a lot of them. And the AUC is kind of correlate with TPR. What is AUC? It's area under the curve, under the ROC curve. So in this graph is called ROC graph. It's a plot of false positive rate versus true positive rate. True positive rate, for example, here is 10% FPR, and the curve shows this blue line is phishing. It has 90. It has around 73% FPR at 10%, 73% true positive rate at 10% FPR. So this plot you can fix at 10% FPR and report the value. Alternatively, you can just marrying the area behind each curve. Of course, the larger area is the better. The better the performance is. Using AUC, the area and the curve, and the performance metrics can avoid truing a specific decision threshold for classification. So you don't need to tell the false positive rate. Here are some discussion by me, the pros and cons. Pros. The paper indeed developed a very useful statistical model to determine whether attack is whether the login is an attack or not. Also, the author validated the system using real life login data from LinkedIn, and according to the author, it's probably the first systematic study of this type of login validation attempts. Lastly, the author mentioned that only a small fraction of login need verification. This is actually very useful because my personal experience, for example, the Canvas, it needs a lot of verification. Like every day when I'm trying to re-log in, I need to verify that it's kind of a waste of resources. The cons. The scope of use is not very clear in the paper. The author didn't discuss whether this is more suitable for like a banking industry or social network or other industry, because different industries, they have different standards. Banking is probably the most strict, and authorizing an unseen event based on probability may not be the best practice for it, and the 10% FPR is a bit high in my opinion. So if you look at the curve, 10% is here, but if you decrease to a lower number like 1%, the performance is not that good. So 10%, what does that mean? It means if the attacker tries 10 times, one of it may go through the process. So that means for some sensitive data or industry, this probably is way too high. Lastly, I think the paper. The paper provided a very interesting statistical model, and it doesn't need to use the attack data from the user's previous login history, but But in terms of the features or criteria, it's actually quite common, and I feel it's already used in a lot of model. For example, I think IP is like every website now is using IP address to determine whether the attack is interesting. So from this point of view, the paper provides a useful model, but it's not something breakthrough, and it's not something can reshape the fields. And more thoughts. I think in addition to those criteria, some more defense can be achieved using post-login activities, because the hacker, when they log into accounts, they have some purpose. For example, take over account or transfer money, and if they do this kind of activity, it means it's more questionable though the login is successful. And also I'm thinking we can correlate with the allowed user activity with login probability score. So what does that mean? If it's a strong login, then you can do anything in your account. If it's a weak login, like from another IP address or from a different country, then even the user is even the login is granted, we should limit it there. We should limit the user ability, like limit the user ability to change the email address or transfer money. And if they want to do this, they need further verification. Lastly, I think this is obvious. You need to alert the account owner of any critical account change. This will definitely make the accounts more the accounts more secure. Why I'm mentioning this? Because in my personal experience, I have my IHG account and Blizzard account hacked before, and both of them, I never received any email from those accounts saying my information was changed. And especially for IHG account, I think it's very unsecure because the password is only a 4-digit PIN. It's very easy to break by a hacker. And by conclusion, the paper is actually very interesting. It provides a lot of details about how the user login should be scored or assessed to determine whether it's valid or whether it's valid. Besides, the paper also systematically studied the effectiveness of the system using real-time data, and according to their discussion, it's probably the first attempt in this field. Lastly, the paper studied the potential attacker to such a system, including targeting the classifier itself, and this will help us to build a better classifier to improve the model. Yeah, that's everything. Thank you very much for listening.